Hello and welcome to the second part of our lecture regarding light-emitting diodes. Let's recall that on the first part of this lecture we looked at the concepts of the injection rate Ri, and we also talked about the lifetimes, right? So the non-radiative recombination lifetime, the radiative recombination lifetime, which are associated with non-radiative recombinations, in which the difference in energy is given off as heat or as phonons, and in the case of radiative recombination lifetime, in the radiative recombination, the energy is given off in the form of a photon with energy hf, and we saw the expression to calculate the total recombination lifetime tau as a function of the other two. On this part we're gonna keep talking about this concept, and we will also look at the dependence of the emitted optical power with respect to the direct polarization current. So still talking about the recombination lifetimes, if tau r is much smaller than tau nr, then the radiative transitions will be faster and therefore will happen at a much faster rate. So you have many radiative transitions in a given amount of time and only a few or fewer non-radiative transitions. So for a light source, that's usually what you want. So therefore the prevailing recombination type, which can be either radiative or non-radiative, is the one with the fastest rates, because you have more per unit time, right? That should make sense. So here on this table we see a list of the radiative and non-radiative recombination lifetimes for three different materials, which are silicon, gallium arsenide, and gallium nitride. And looking at silicon, for example, we see that the radiative recombination lifetime is of the order of milliseconds, and the non-radiative recombination lifetime is of the order of the nanosecond. So a million times smaller, and therefore this means that the non-radiative recombination rate is around a million times faster from what we've just discussed. So at any given interval of time or period of time, you'll have a certain amount of radiative transitions, but many more, right, non-radiative transitions, and that's associated with the indirect band gap and with the fact that silicon is an inefficient material to be used in light sources such as LEDs and lasers. Now for gallium arsenide, on the other hand, both the radiative and non-radiative transition lifetimes are around 100 nanoseconds, so of the same order. So you have similar rates, right? And therefore for each non-radiative recombination you'll have one radiative recombination. So it should make sense that half of the recombinations will result in the emission of photons, and this means that gallium arsenide is a good material. So that's the parameter, right? A good material to use as a light source. For gallium nitride, again, you see that the radiative recombination lifetime, which is around 10 nanoseconds, is much larger than the non-radiative recombination lifetime, so 100 times larger. So certainly gallium nitride will not be as good a material to make light sources as gallium arsenide, although it's somewhat better than silicon. And this leads us to the definition of the internal quantum efficiency. So eta I, right? Eta I is the ratio of the radiative recombination rate to the total recombination rate, right? So it's the percentage, or it's the ratio of the recombinations which will lead to emissions. So from this definition we see that eta I is going to be RR divided by R total, which is RNR plus RR, And if we consider that, you know, the recombination rates are proportional to 1 over tau and substitute here, we get this, right? Eta I is equal to tau, the total recombination lifetime, divided by tau R, the radiative recombination lifetime. So this is the expression to use right here. And it is, as we've said, it is the fraction of the total amount of recombinations which will lead to the radiation of electromagnetic radiation, right? So if we plug in the numbers for silicon, and remember, to calculate this, we need to get the total tau, which can be obtained from this equation right here. But if we plug in these numbers, these values, we get eta I equals to 0.001%, which means that only this percentage, this very small percentage of recombinations, will lead to the emission of photons in silicon. Whereas, you know, if we plug in the numbers associated with gallium arsenide, I should point out that this is for gallium arsenide right here, and this is for silicon, then we get, as we said, 50%, right? So 50% of the recombinations in a gallium arsenide will be radiative recombinations, and therefore will lead to the emission of photon. Only materials with large internal quantum efficiency, eta I, you know, ranging from 20% to 90%, typically are used to fabricate light sources, or, well, no, can be used because they will make efficient light sources such as LEDs and lasers. Now, lastly, for a light emitting diode, it's usually desired to know how the emitted light power behaves as a function of the injected current I. So what you usually have is a directly polarized diode, right? Of course, you must have a current limiting resistor of some sort, but, you know, just in a simplified picture, you need a directly polarized diode in which the direct current, you know, due to the recombination inside the active layer of diode, is going to be responsible for making the emission, spontaneous emission process possible. And for a given current, you have a given emitted optical power, and we wish to know how this optical power behaves as a function of I. In other words, what is the function that describes this emitted optical power with respect to I? You know, and it turns out it's a linear function. So if you increase up to a certain point, if you increase the direct current, the emitted power will increase linearly, but still we wish to know what the proportionality constant will be. So let's derive this. We have seen on the first part of this lecture that the injection rate, Ri, is the rate with which excess carriers, you know, excess electrons and holes are injected inside the active region, which is the depletion layer of the p-n junction. So the rate with respect to time with which these excess carriers delta n are injected. So just to, you know, if we have a forward bias diode as illustrated here, this forward current is responsible for injecting holes and electrons in the depletion layer or in the active layer. And the recombination of these electron-hole pairs will be responsible for light emission. Because of this current, you have an excess of electrons and holes being injected per unit time, you know, so delta n is the excess electrons and holes which are injected due to the current I. There will be a rate of injection per unit time, and that's Ri. And we've also seen that this rate is equal to the excess carrier concentration divided by the total recombination lifetime, right, as we've argued before. So we have an expression for the injection rate. Now the injected carriers, as we've just seen, are supplied by the source through the direct or forward current I, right? And we can also express injection rate Ri, should put an I here, as a function of this current. And if we think about it, if current is the rate of electric charge in coulombs per unit time, which is flowing through the wire, through the diode, if we divide the current by the elementary charge E, we get the number of injected electrons or holes, the number of injected carriers per unit time, right? Current is coulombs per second, so charge per unit time. If we total charge per unit time, if we divide the total charge by the charge of one electron, we get the number of electrons per unit time. This is this term right here. But right, the injection rate, like many other quantities that we're dealing with, are normalized with respect to the volume. Also, we in order to get this expression for the injection rate, we also need to divide this by the volume of the active region, the volume of the depletion layer. This is also true, and this is another expression for the injection rate. And we can write this because every charge injected by the source through this current is being consumed when the electrons and holes recombine at the junction. Now, the number of radiative recombinations per unit time multiplied by the energy of a single photon will give us the generated power. And the number of radiative recombinations per unit time is equal to the number of recombinations multiplied by the internal quantum efficiency eta I, which we've just seen. If we assume that all of the injected electrons are recombining at the depletion at the active region, then we can say that the total number of recombinations, number of recombinations per unit time is equal to I divided by E, the elementary charge E, the charge of the electron. Because again, right, if we divide the current, which is charge per unit time, by total charge per unit time by the elementary charge, we get the number of carriers per unit time, electrons and holes which are injected in the junction. And if this, if every electron and every hole recombines, which will not be true, generally, if the polarization voltage is too high, then there might be some leakage current, but otherwise we can safely consider this, and this is the total number of recombinations per unit time. And if we want, the total number of radiative recombinations per unit time, we just multiply this by the internal quantum efficiency, because this is the fraction, right? Fraction of radiative recombinations with respect to the total number of recombinations, right? And therefore this will give us, so if we multiply this by eta I, we get the number of radiative recombinations per unit time. Hopefully this logic makes sense, and therefore the number of radiative recombinations per unit time can be given by this. So I divided by the elementary charge multiplied by the internal quantum efficiency. And if we multiply this, right, this is the number of radiative recombinations per unit time. If we multiply this by the energy of a single photon, a single emitted photon, if we have the total number of radiative recombinations and we multiply this by the energy of a single photon, we will have the total energy. And since this is the total number of radiative recombinations per unit time, this will give us the total energy per unit time, which is power. Does this make sense? So, using logic, we can derive this expression. So the generated power, P gen, will be equal to this. What we've just done is related the optical generated power to the current, the forward current I, right? And if we put this in evidence, that's what we have. So all of these terms will be a constant for a given material with a given gap and a given internal quantum efficiency. But this, as we expected, gives us a linear relation between the generated power and the polarization current I. So if you increase the forward current I, you should expect the emitted power, the optical power, to increase proportionally. This is just the expression we desired to begin with. It's important to note that dominating emission mechanism in LEDs is spontaneous emission, because usually, you know, the difference between the Fermi level associated with the conduction band and the Fermi level associated with the valence band will be smaller than h times f, which is the photon energy, and therefore you will not have population inversion, so the stimulated emission will not be significant. Also, you know, the fact that light power can be lost through different mechanisms has not been taken into account in this expression right here, right? This is just the power generated by radiative recombinations inside the active region, i.e. the depletion layer. But this light, you know, if we consider all of the light that is generated, some of it can be lost due to reabsorption, scattering, reflections. So you will not be able to use or efficiently extract all of the light that is generated to the outside world to be used in a given application, right? So some light is lost, and this needs to be taken into account as well. So how can we do this, right? So different mechanisms contribute to the fact that a portion of the light power does not exit the structure of the diode. The extraction efficiency, which is different than the internal quantum efficiency eta I, the extraction efficiency eta E, which will also be a fraction, so a number between 0 and 1, is the fraction of the generated power which effectively exits the diode and can be used for different applications, right? So again, eta E is going to be 0 point something, number between 0 and 1, and the facts that contribute to decreasing eta E, right, from making it different than 1, smaller than 1, are absorption. So if you consider a regular p-n junction in a diode, you have the band gap in this region with the conduction and the valence band, and just as easily as the recombination process, right, in which an electron recombines with a hole, loses energy and emits a photon with energy hf, this same photon can be reabsorbed by an electron which is initially sitting down here and absorbs this energy, right? So annihilating this photon by generating an electron-hole pair. So the photon is annihilated and the electron gains energy and rises up to the conduction, to an empty state in the conduction band. So these will be concurrent processes, right? Absorption, in which the photon is annihilated, will be a concurrent process with stimulated emission. These processes will keep happening. So absorption is an issue, and part of the light that is generated by stimulated emission will be reabsorbed by the material, except, you know, if you use a double heterostructure and the gap of the outside semiconductor is larger than the energy of the emitted photons, then this can be decreased, right? The absorption rate can be decreased. So if we recall that in a double heterostructure, you know, the recombination of an electron and a hole will lead to the emission of a photon with energy equals to hf, which is just the difference in energy, the initial energy and final energy of the electron. This is the delta E, right, which is equal to hf, is the energy of the emitted photon. In order for this could be reabsorbed in the active region, which is again, right, this middle layer right here in the case of the double heterostructure. But this photon cannot be absorbed in these adjacent layers right here, right, the heavily doped p-type and n-type semiconductors, because the band gap is too large. So if an electron is sitting down here, this delta E is not enough to make the transition up to the conduction band possible, because this energy here is too large. So if you call this delta E dash, this delta E dash is much greater, or is greater than delta E. Therefore, this energy that this photon could provide, right, if it's like this delta E, it would only be enough to raise the electron in energy, so to speak, up to an imaginary level right at the center of the forbidden energy band. But this cannot happen, and therefore absorption will not happen here, and it won't happen here as well, right? So it is like these outside layers are transparent to the emitted photons, and this decreases reabsorption significantly. So this is still yet another advantage of the double heterostructure. So absorption is an issue, and reflections at the semiconductor air interfaces. So you have these different layers will have different refractive indexes, and the device itself has a refractive index which is much greater, you know, a permittivity, an epsilon that's much that is different than air or the outside worlds, and therefore light will be reflected, and some of this light will be lost, aside from Rayleigh scattering and scattering at the interfaces. So typically the refractive index of these semiconductors is around 3.4, and for air it's around 1. So in the best case scenario with normal incidence, you have 32% reflection, right? So, you know, around 70% of the electric field actually comes out of the device, and this will translate in some power loss. And therefore all of these factors contribute to this eta E, which is typically around 0.2 to 0.3, and in order to effectively calculate the power that comes out of the diode, we need to multiply the generated power, which we've just seen to be this, right, eta I times HF over E times I, by this extraction efficiency. And it's usual to define an external efficiency, which is the product of the extraction efficiency and the internal quantum efficiency. So, you know, we see here again that the power coming out of the device has a linear relationship with the forward current I, up to some point, because if you raise the polarization voltage too much, the device will begin to heat, and then, you know, the total non-radiative recombination lifetime will decrease, and the internal quantum efficiency will begin to decrease as well, and then this linear relation will begin to saturate for some output optical power. But, you know, for most of the typical current values that we are interested in when we're polarizing an LED, the relationship should be very much linear. Finally, we should distinguish between the two most common type of LEDs that exist, right? With respect to structure, LEDs can be classified into edge emitting LEDs, so ELEDs, or surface emitting LEDs, or SLEDs, S or SLEDs, right? In ELEDs, the double heterostructure will usually be used to constitute a slab waveguide. So, for example, you might have the wafer here, and, you know, the heavily doped p-type semiconductor here, the active layer, the lightly doped p-type or n-type semiconductor here, and the heavily doped n-type semiconductor here. Now remember that in a double heterostructure, the band gap of these external layers, which are on either side of the active layer, the band gap is larger, and this means that the refractive index is usually smaller. Therefore, the active layer will have a higher refractive index, and it will be able to confine an optical mode, a transverse mode here. And therefore, if this is the chip and this is the surface of the chip, the top, the light is being emitted from the edge here. So that's why it's an edge emitting LED. So you have the chip, and the light is coming from the side of the chip. Now the exit solid angle in ELEDs is smaller than the solid angle in surface light emitting diodes, right? This means that the light will be coming out in a more directional manner. So in surface light emitting diodes, light is emitted through the surface of the chip. So it is like you have the PN junction or the heterostructure here on top of the chip, and the light that's coming out of the device used in different applications is the light that's coming out from the top. And this, because there's no waveguide involved, again, this is a light that has a much broader solid angle than in ELEDs, right? And it should be said that an opening in the top metallization layer is what allows the light to pass through. So you need metal contacts here, right? And there should be an opening in order for light to come out. From what we've said, it should be clear that edge emitted light is lost in surface light emitting diodes, and the vertically emitted light is lost in edge light emitting diodes. Okay guys, so this was it for today's lecture. On our next lecture we'll talk about lasers. So we'll begin our discussion about lasers, and stimulated emission and lasers. So thank you very much for sticking around, and I'll see you on our next lecture.